Hello all of you. Welcome to the 12th lecture on the course on analysis and modeling in chemical engineering. In this lecture, I will continue on the discussion on the phase equilibrium for a multi-phase multi-component system, and then I will introduce the idea of degrees of freedom also in this course, and from there I will derive what is known as the Gibbs freeze rule, and we will do some examples on that. So, in the last week and in the last lecture, in continuation of last week, we have basically discussed all the fundamental laws and concepts in chemical engineering, starting from equation of motion, transport equation, material balance, energy balance, thermodynamics, chemical kinetics, chemical equilibrium, and phase equilibrium. And now it is time to put them all together in practice for simulations or modeling of processes. So, there is one thing that is very important, and this is a general mathematical concept rather than being true, only valid for chemical engineering, is the idea of or notion of degree of freedom. Right? The degree of freedom defines that what are the number of free parameters that can be varied independently in the system. In fact, we have encountered this in one example in thermodynamics, where we referred to the degree of freedom of a molecule. For a monoatomic gas, it was 3, that is the number of directions that it can go to. But we can also define degree of freedoms for mathematical equations in the following way. We can define the degree of freedom as the number of variables or unknowns that we have in the system of equations, and here the type of equations are not very important here, although I am giving an example of simple linear equations, but it can be any equation, but number of variables is what is important and the number of equations is what is important. Right? So, the degree of freedom is defined here as the number of variables or unknowns and the number of independent equations. Right? Independent word is very important. If, for example, you have equations which are dependent on each other, that means they can be written as some linear combination of the other equations, then they are not considered independent. Let us take, for example, x equal to 2 and 2x equal to 4. They are same equations. If I double the first one, I will get the other one, right? So, clearly the number of equation in this case is not 2, but 1. Similarly, if you have, let us say, x plus y is equal to 2, and let us say we have y is equal to 1 and x equal to 1, the third one I can get from the first two. So, the third one is not an independent equation. In fact, I can consider any of them to be dependent on the other. If I, for example, know the second and third, the first one is not independent, right. So, therefore, here we have only two independent equations. So, we always refer to the number of independent equations as the equations which are not a linear combination of other equations in the system, and it is very important and we have to look at it whenever we encounter any equation. So, now if you have certain number of independent equations and the variables, and I am taking an example of a simple linear equation, there are three possibilities which may emerge, right. So, in the first case shown here, we have only one equation and we have two variables x plus y equal to 2. So, if, for example, I want to find what is y, I need the value of x and it has to be specified to me, it cannot be an unknown. Similarly, if I want to find the value of x, I need to be told what is y. So, y is something now which is can be freely defined. Y is free to vary, because the equation is only telling me that if I know y, I can find x, or if I know x, I can find y, right. So, one of the parameters x or y, or one of the variables here x or y, they are basically free to vary, and the other one comes from the equation, right. So, what we say here therefore is the degree of freedom of this system is the number of variables, which is 2, minus the number of independent equation. You see the equation is only 1, so it is of course independent, that is equal to 1, which is more than 0. That means either x or y needs to be specified, and this system as it is, unless I give the value of x or y, the system as it is what is known as under specified system. Now, I take a second example where we have two equations and two variables or unknowns x and y and two equations, and now the degree of freedom is actually number of variables is 2, number of equations is 2. So, degree of freedom becomes 0. In fact, I can solve it and get the value of x and y. And now, I no longer have the liberty to choose x and y whatever I want to do. In the previous case, I had that liberty. Now, x and y are defined by these two equations, right. So, therefore, there is no degree of freedom in the system. I cannot choose any arbitrary any value of x and y. So, the system is now called well specified system. Whatever equations we have, they can be solved to find all the variables or unknowns in the system. Let us take now the third example where we have three equations, and the first thing we should check is whether they are linearly dependent in some way, and you can figure out that it is not. If I add the first and second equation, I get 2x is equal to 3 by adding the first and second equation. That is not same as the third equation, right. That also tells me that something is clearly wrong, because 2x equal to 3 and x equal to 3 both cannot be true, but that is besides the point, right. So, these three equations are not linearly dependent. So, we have three independent equations, but we have only two variables, right. And this gives a DOF of -1, which is less than 0. That means we have too much information given in the problem, and in this particular case, the problem does not have any solution. And you can see from here, if I add 1 and 2, we get 2x equal to 3. The third one gives me x equal to 3. So, clearly the third equation is conflicting with 1 and 2, and therefore, there is no solution in this problem, and we say that the system is over specified. So, whenever we look at any problem concerning material balance, or in general any problem where there is some mathematics involved, we have some equations involved, the first thing that we need to ensure is that the degree of freedom is equal to 0. If, for example, if it is more than 0, then we need to know which are the variables I want to specify in the problem or give the user input, or I have a freedom to vary whatever I want it to vary, right. But otherwise, if I do not have that information, that which one I want to freely vary or which one should I know, in that case there is a problem, right, because we do not know which parameter do I need to vary and things like that, right. Okay. So, now go back to the example of this multi-phase multi-component system. I have written down the equations in the previous lecture. We had the thermal equilibrium, mechanical equilibrium and phase equilibrium together, three different equations, and I will show you again in the next slide. But here we list the variables in the problem. What are the variables? Because we want to find the degree of freedom. So, we have to figure out what is the number of variables and then what is the number of equations, independent equations in the problem, right. So, what are the variables? So, we can define temperature of each of these phases, and therefore, we have p such temperature variables. We can define the pressure for each of these phases. So, therefore, we have p such pressure variables. We can define composition of each of these phases, assuming that each phase is consisting of all the components. So, therefore, we can define C mole fractions for each phase. So, in total for p phases we have Cp variables. Again here subscript is for the component. So, I stands for the component and the superscript, it is indicative of the phases where it is in. And just like I define the mole fraction, I can also define chemical potential now for every component in every phase. And just like we have Cp mole fractions, we also have Cp chemical potentials that I can define for that system. And if I now add or count the number of variables in the system, we have 2 Cp plus 2p variables in the system, right. There are two important points here I again emphasize. The first, there is no chemical reaction being considered here. One can do that, that will make things more complicated, but what I will discuss on the phase equilibrium, there is no chemical reactions. And the second thing which I did not explicitly specify earlier, is that we are considering only the intensive variables, right. If you look at it here, none of the quantities which I have listed depend on the quantity of how much is there, right. Temperature is independent of quantity, pressure is independent, mole fractions are independent, chemical potentials are also independent. What this means eventually is there is nothing that gives me a notion of the size of the system, right. I can have a phase equilibrium in a small vessel versus a phase equilibrium, maybe the same kind of phase equilibrium with the same compositions, but in a larger vessel. But in order to characterize that, I need to consider extensive variables that depend on quantity, right. In here I am considering only the intensive variables. Later on, we will do examples where we also consider the extensive variables in the system, right. And the other thing that you see here is if you have actually a multi-phase, multi-component system in the chemical industry, I was showing you examples earlier of distillation column and so on. In that case, you have to worry about the feed, inlet and outlet and all those things. I am also not considering that, and you will see why that is a problem, because I am considering only intensive variables. So, I cannot consider the feed, inlet, outlet and those things, right. So, you can think of it as a batch system where the phases are in equilibrium, or you can also think of it happening in a continuous system. There is a feed, inlet and outlet, but right now I am not considering them in our description, but we will see how to consider that later. So, going ahead, this we have already done. So, we wrote the equations for the equilibrium in this system. Thermal equilibrium gives me P minus 1 equations, that is temperature equalities, P minus 1 temperature equalities. Mechanical equilibrium gives me again P minus 1 equations, again P minus 1 equalities, right. I purposely represent the pressure as small p here to differentiate from the number of phases P. Earlier in the previous lectures, I have used capital P for the pressure. Just to make our convention easier, I am using a small p here. And then the phase equilibrium, we have C into P minus 1 equations. And then finally, as I was telling you, the chemical potential comes from the Gibbs free energy, and the Gibbs free energy comes from the equation of state or the property relations. So, therefore, chemical potential has to be some function of the compositions, and now I am referring to composition as the concentration or mole fractions of all the variables, all the components in the system in a given phase, right. So, for example, I am talking about a phase that contains, let us say, sugar plus salt plus water, then the chemical potential of, let us say, sugar in this phase is going to be a function of the mole fraction of sugar, mole fraction of salt and mole fraction of water, right. That these three together defines the composition of that particular phase, right. So, therefore, I put a curly bracket here to indicate that I am referring to not only the mole fraction of component I, but mole fraction of all the components in that particular phase. So, I will do that, and there is some function that comes from the equation of state. I gave you examples of equation of state like ideal gas law and van der Waals equation of state, but for liquids there are more complicated equation of state. You may have heard of Redlich-Kwong equation of state, Peng-Robinson equation of state, right. There are further ones, more detailed ones like NRTL, Unifac, Uniquark. Whatever we are doing for that, that has to come from some experimental data or experimental analysis. That particular thing I am using here. So, this function, although it looks quite harmless, in fact it is quite complicated, because the function form can be quite complicated, but nonetheless it has to come from the equation of state. But I again want to emphasize to you that if your process calculation or process simulation is going wrong in anything that you are doing, the main culprit which I will expect is the equation of state that you are using. If, for example, you are doing everything perfectly, but you assumed an ideal gas law for water and sugar or any complicated system like wastewater, then I can say without any hesitation that whatever you have done is wrong. So, equation of state, although I am writing in this particular way, it may appear to be simple, and I am not going in details about different kinds of equation of state or my recommendations for this, but this is the area where things can really go wrong, right. So, take that equation with very seriousness and choose the proper of equation of state if at all you are doing any process simulation. And finally, I have told you there are summations of mole fractions. So, in every phase all the mole fractions must sum to 1, right. So, if I count the number of equations in this case, I will get something like 2 Cp plus 3p minus C minus 2 equations, and we already have figured out how many variables do we have in the system. So, I now do number of variables minus the number of equations, and what I get is the degree of freedom of the system. So, this is the number of variables, this is the number of independent equations, and this gives me C minus p plus 2, right. I am assuming that the equations whatever I have framed are independent, right, and indeed in this case the way I have written it is independent, but in general you need to do this check whether you are writing any extra equation, right. So, if your DOF is not equal to this, maybe you are counting an equation which should not have been counted, it is a linear combination of other equations in the system, right. But this is a general rule that DOF is equal to C minus P plus 2, it is called the Gibbs phase rule, which is true for any multi-phase multi-component system as long as it is non-reactive and as long as we are considering only the intensive variables in the system. Yes, I will take an example of the phase diagram of pure water that you may have seen in the thermodynamics courses, just to demonstrate the application of Gibbs phase rule, right. So, if you have seen that diagram, you may recall that the pressure versus temperature relation looks something like this, where you have a vapor or a gas phase here, a liquid phase here, and a solid phase here. And if I am looking at a pure water, then the number of components is naturally equal to 1, right. Solid forms at lower temperatures and higher pressures, and if I am in the solid phase, that is the ice phase, clearly my P is equal to 1. Liquid forms at higher pressures and also higher temperatures, right. So, but I mean like if temperatures are much higher, then we are also going to form a gas phase, right. So, a gas will actually form at lower pressures and high temperature, and liquid is somewhere here, right. So, when we have like water as a liquid, in that case again P is equal to 1, and when we have water as a water vapor, that is gas, here also P is equal to 1. Eventually, there is a critical point and there is a continuous transition beyond the critical point, but let us stay below the critical point. We can discuss about it, or you may have seen this in the thermodynamics course. So, I am not going beyond the critical point, I am staying below the critical point, right. So, now clearly for liquid, water or ice or water vapor, P is equal to 1. So, what does Gibbs phase rule tells me? It tells me that my DOF is equal to C minus P plus 2, which is C is equal to 1 minus 1 plus 2. That means, I have a freedom to specify 2 variables in the system. What are those 2 variables? It is pressure and temperature in this example that I am showing here. I can choose both pressure and temperature independently. Let us say I am in the liquid phase and I look at this point, this point, this point or that point, right. All of them have different values of pressure and temperature. So, I can arbitrarily choose the pressure and temperature values as long as they are within the limits where we are forming the liquid phase, right. But then if I am, let us say, lying on one of these lines are referred as coexistence lines, coexistence line or curve, right. So, all of them are coexistence one, right. This one is the solid liquid coexistence line, this one is solid vapor coexistence line, and this one is liquid vapor coexistence line, right. The solid liquid line is also called a freezing curve, solid vapor is also called sublimation curve, and liquid vapor is also called the boiling curve, right? But that's besides the point. Right? What this means is that there are two phases in equilibrium here, right? Just to demonstrate this idea, let us say, for example, I start from this point, let me call this point A, and I keep pressure fixed, but I raise temperature. So, I am eventually going to cross this line and come to a new point B. That is a process that is isobaric. At constant pressure, I am raising temperature of a liquid. What do we expect? The liquid will eventually become vapor. So, A is liquid, B is vapor, but in between we are hitting this curve at, let us say, some point Q, and at this particular point Q you have a coexistence of liquid and vapor together, right? Similar thing I can do it for solid liquid curve and solid vapor curve, right? So, if we are on coexistence curve, right? So, in that case my P is going to be 2. Now, two phases, whether it is liquid vapor, liquid solid or solid vapor, two phases in coexistence. So, now we have DOF is equal to C minus P plus 2, C is still 1, but P is now 2 and there is a 2 there. So, it becomes 1. So, now we have freedom to choose only one of the parameters. Why is that, right? So, think about it. If I am drawing a point along the curve, let us say these points, as soon as I choose a point on the curve, it becomes like something where if I specify temperature, the pressure gets specified because I am on the curve. So, let us say this point correspond to a certain temperature, but now for this temperature I need to be at a certain pressure to be on the curve. Let us say I choose this temperature, then I need to have a certain pressure to be on the curve. In other words, for any given temperature, the coexistence will happen only for a pressure that is a unique pressure that is a function of this temperature, and I can say the same thing for temperature being a function of the pressure, right. So, now I can choose either T or P. Let us say boiling point of water. As soon as I say 1 atmosphere, at 1 atmosphere the boiling point of water is close to 100 degrees Celsius. If I now raise the pressure, the boiling point is going to change, but the boiling point will be a function of the pressure. So, now if I am on the boiling curve, then as soon as I choose the pressure, the temperature automatically gets defined. Similarly, as soon as I choose the temperature, the pressure automatically gets defined, right. So, now we look at this special point where these three curves are meeting. Let me call this point something like TR. This is called a triple point. At triple point, now we have a coexistence of three phases, because here solid, liquid, gas, three regions are meeting together. At this point, we have therefore SLV. So, at triple point TR in the curve, we have P is equal to 3. And now, what is the degree of freedom? Degree of freedom is 1 minus 3 plus 2, that is 0. Now, we do not have a freedom to choose either temperature or pressure, right. Why is that? It should be obvious from the curve that this triple point corresponds to a particular value of temperature and a particular value of pressure, right, and that value is fixed for water. I do not have any liberty to change the triple point, right. I do not have a liberty to choose the pressure and temperature condition at the triple point. They are specified for water. Of course, if there is some other liquid, it may have a different triple point or may not have it. That is a secondary issue, but for pure water, you are going to have a fixed value of pressure and temperature. So, there is no liberty to choose either temperature or pressure. It is defined by the system, and the degree of freedom is equal to 0 for this system. I can go ahead and now take an example of a distillation process where now we have a vapor and liquid in equilibrium. There are two phases in equilibrium. But what I also want to consider now is the effect of the feed that is coming in, the liquid that is going out, the vapor that is going out from top and some heat that is being supplied. Now, as soon as I draw this, right, one thing that one has to keep in mind is now I am looking at a continuous operation, and the thermodynamic equilibrium definition that I have given earlier, that was basing on the fact that we have no external agency in the system. So, no pumping, no flow, nothing is there, right. So, the idea of equilibrium therefore is not really a true equilibrium, you can call it. It is some kind of, we can refer as some kind of a pseudo equilibrium. That means we can still apply the equations of equilibrium, but with a caveat that it is not strictly in thermodynamic sense that equilibrium, but still the equations may be valid, maybe with certain corrections, right. So, now I can again do the Gibbs phase rule for this example, and when I am doing that, I will consider only the conditions within the distillation column, right. And you see, whatever equations I have written now are pretty much the same equation that I had earlier for a multi-phase multi-component case, but I am writing the variables only for 2 phases instead of p phases, right. Number of component is still c, but I am writing only for 2 phases. As a common notion, we say x as liquid mole fraction and y as vapor mole fraction, and we are defining chemical potential for vapor phase and liquid phase and things like that. So, pretty much there is no change in the definition of variables, and accordingly there is no change in the definition of the equations. We still have the same thermal, mechanical, chemical or chemical potential equilibrium. Again, there is no chemical reaction, right. Again, we have property relations, and again we have summation equations, and essentially we recover the same Gibbs phase rule, right. What this means is that there has to be now something else in order to consider these effects, right. And if you look at these quantities, it is not very surprising why we have left them out. The feed rate, it is an extensive quantity. The vapor flow rate, it is an extensive quantity. Liquid flow rate, it is an extensive quantity, right. So, we are considering only intensive variables. Of course, the feed may have certain temperature and pressure and maybe some enthalpy per unit mass or mole of the feed. These quantities are intensive in principle, but there is no way to consider that if I do not consider the feed. What I will show you next is we have to write the material balance for this system, and that becomes an extensive equation, not an intensive equation. So, therefore, I will not include this in the intensive variable picture, and I have defined Zi as the mole fraction of the component in the feed. There is a reason why we are calling it Z. We are reserving X for liquid, Y for the vapor, but we are saying Z for the feed, because the feed can be either liquid or vapor, or it can be multi-phase already. It is already a mixture of liquid and vapor, right. So, therefore, we say Z as the overall mole fraction in the feed. That is the notation we typically use in distillation problems. Now, let us consider all the variables and try to see what other equations will result. We already have figured out the equations concerning the intensive variables. Now, I am looking at the equations concerning the extensive variables as well, right. So, I will consider also now some of the intensive variables which we have ignored earlier, because I was telling you that I cannot consider them unless we consider the feed, vapor, liquid and the heat supplied, right. So, now I am also considering them. You see also a notation here in terms of this enthalpy per unit mole. So, I am using a small h here, a small h here and a capital H here. Capital H, I am typically using it for the vapor phase, right, and small h I am using for the liquid phase. In this case, in principle, it can be small or capital, but I am keeping it small because the feed can be liquid or vapor or a combination, right. So, what are the additional variables? The additional variables now are the overall mole fraction that is entering the feed of all the components. So, we have C such variables. The temperature and pressure of the feed. So, we have 2 such variables. The enthalpy per unit mole of the feed that is coming in, and enthalpy per unit mole of the liquid that is going out and the enthalpy per unit mole of the vapor that is going out. I can also define in terms of per unit mass, but I am defining as per unit mole. What is this enthalpy? This is the energy that the feed is carrying into the system. It may have been preheated. So, when the feed comes in, it comes with that thermal energy, right? That is an example of the enthalpy that is carrying in the system, right? It is a continuous system, unlike the case of chemical equilibrium or the examples which I did in the basic thermodynamics. This is a continuous system. So, therefore, the notion is a bit vague compared to whatever we have discussed. What we are saying here, that the feed carries some energy in the system, liquid takes away some energy along with it, vapor takes away some energy along with it, and we are supplying some heat, and those energy being carried is represented by the enthalpies. And now we have 3 molar flow rates and also a net heat supplied or taken out from the system. It depends whether we are taking away heat or giving heat depending on the requirement, right. So, I am here doing it for only 2 phases, but the counting I am doing considering a general P, right. So, we have C mole fractions, overall mole fractions, 2 additional thing because the feed is the same as long as we have a single feed. But then if you have, let us say, P phases, then you will have P plus 1 outlet streams, right. So, let us say there is 3 liquid phases. So, you have 3 outlet for 3 liquids, right. But in this case there is only 2 outlet, because in this case P is equal to 2, right. All right. And then similarly, these variables are also P plus 2. There are two phases here, and there is additional feed and heat supplied. So, in total it becomes 4 in this case. So, now I have counted the total number of additional variables that we have got in the system, which is C plus 2 P plus 5. And now I look at the additional equations which will come for the system. What are those equations? These are the material balance for the system and energy balance for the system, right. The material balance can be written for each of the components. Whatever I is coming in the feed is F into Zi. Whatever I is going away with the vapor is V into Yi. Whatever I is going away with the liquid is L into Xi, and we have C such equations for every component. That is the overall balance for each of the component. Then we have a single energy balance, because energy is not separated. Whatever energy that system gets, it's as a whole, right. So, we are doing energy balance on the entire system. We have a single energy balance equation, right. And what is that? It is the energy that is being carried by the feed that is coming in the system, Q that is supplied to the system. If it is taken away, it will be negative. Then whatever is going away from the system, it is either carried by the vapor or it is carried by the liquid. So, we have one energy balance. And now we have this enthalpies, and these enthalpies clearly has to come from again from equation of state, just like chemical potentials, and in this case it is 3, but in general it is P plus 1 for P phases. And again, since we have introduced a new mole fraction variable, we have a summation equation for that overall mole fraction, and we again get an extra equation from here. So, this gives me a total number of equations equal to this. So, if we find the degree of freedom, I now begin with whatever we have obtained earlier, number of variables minus number of equation considering only intensive variables, and now I add whatever degree of freedom comes by adding the new variables minus the new equations. So, this is the new variable minus new equation gives me here P plus 2, and if I add it, I get something like C minus P plus 2 plus P plus 2, so it will be C plus 4. Okay. If I count the number of variable, it is C plus P plus 1, 2, 3, and then if I now subtract, I will have C plus 2P plus 5 minus C plus P plus 3, that will give me P plus 2. So, the net degree of freedom is therefore C plus 4 in this particular case. So, we can go ahead and do multiple examples. Let me do one quick example here. So, if we have a vapor liquid coexistence line of a sugar solution, in that case, unlike pure water, now we have 2 components. We are looking at coexistence line of vapor and liquid. So, we have P is equal to 2 So, degree of freedom is again given by the Gibbs phase rule, C minus P plus 2, and then this becomes equal to 2 for this case. In the case of pure water, it was 1, but now it is 2. Here we can change the maybe the composition of sugar and the temperature together. I can go ahead and do other examples. Let us say I am considering 4 phases and 5 components, and pretty much it is the application of the same idea. I derived a general expression of that system. You can simply try to do it for a certain number of phases. In this case, you have 1, 2, 3, 4 phases, and you have 5 components. So, you have C is equal to 5 here, P is equal to 4 here. The degree of freedom in this case is going to be 5 minus 4 plus 2, which is again equal to 3 in this case, and we can write the equations in the same way that we wrote earlier. And we can also do it for other cases. In this case, we have a 3-phase column. So, P is equal to 3 and C is equal to 4, right? And we have 3 output streams, 1 for each phase. Again, we can draw the system in pretty much the similar kind of way. And again, we can find the degree of freedom as something like 4 minus 3 plus 2. That will give me something like 3. So, with that, I conclude this discussion. What we have discussed in this lecture is how to find the degree of freedom for only intensive variables in a multi-phase, multi-component system, and how the result is going to change if I also consider extensive variables in the system, right? And then I took some examples to demonstrate the application of Gibbs phase rule. So, with that, I conclude this lecture. Thank you so much.